time to check out the heat transfer unit operations class. As the name implies, we're going to be talking about how heat transfers in industrial operations. So I got this huge heat exchanger. Actually, it's a shell because it has a huge tube and shell and tube exchanger. It has plenty of tubes, each one of these holes. It's a long tube that goes backwards like this way. So in this section we study what is the industrial application and how we heat in like huge scales, very big, large materials, amount of materials, tons per second, tons per day, etc. And yeah, essentially it's about that. If you recall all the heat operations, we talk about heat exchangers, boiling, condensation, and yes, I will say those are the most common, but of course you can have freezing, you can have melting. Melting, probably metallurgy, or any that produces metal, you need to burn down and then have this mold, and then you got your ingot. Then for freezing, probably you are more into, say, cryogenics or anything related to food. So what is inside of this subject or course, heat transfer operations? And I must recall, or let's say, I must warn you, this is essentially for the chemical engineer. There's also a lot of heat transfer for the mechanical engineer and all the process engineers that you might imagine. But this is more for the, let's say, more about the chemical engineer. And we use a lot of substances to make heat transfer. So once again, here goes an exchanger. It has no shell. It's been removed. But you can see all the tubes inside. The tubes will make, let's say, will exchange heat with the outside fluid. So here we have the shell, and we have all the tubes. So the tubes go in. Then we send all, this is the hot fluid. Let's say it's very hot, super hot, and this is not that hot. And this is cold. And then goes here, and then it's no longer that cold. Then, first things first, you will need to know a little bit on the theory on how heat transfers. So, for example, you're probably seeing a lot on thermodynamics on heat, a lot of mass balance and energy balance, mainly energy balances, how we relate Q to change on enthalpy. We have reaction enthalpy, we have fuel or combustion enthalpy, we have formation enthalpy, we have sensible enthalpy, we have latent heat, which is essentially change of phase enthalpy. So we know that heat many times implies enthalpy changes. And then we saw in transport phenomena how we have, let's say, a temperature gradient, how it's very high here, very high, and then it's not that high. So we see how it changes along the length. So for instance, we have this, let's say we have 50 Celsius of the hot fluid, and it goes out at maybe, 25 Celsius. This is, let's say, 5 meters long. So we have this gradient that we have a loss of 25 Celsius because it's 50 minus 25 divided by 5 meters, so this is 5 Celsius per meter in average. So we're interested in that as well. So we have three very famous heat transfer mechanisms. We have conduction, which is, let's say, you have direct contact of a solid with another solid. This is very common for, let's say, in the lab, you have this beaker and you have this balance which can heat. So you have direct contact of the metal plate with direct contact with the glassware. Then it comes convection, which is a little bit more interesting. Convection is about fluids, liquids and gas as well. So I like to give this example. You have your oven or whatever, so it starts heating up. So all the air is going up naturally because it's less dense, so it goes up and it starts heating the cold air, which is here, so it goes and keeps going. Cold air typically goes down, hot air goes up. And radiation. So if you've been doing some barbecues, you know that you have your barbecue right here, and you have these little metals. So we have three types of heat transfer. I will say 5% or less is conduction via these little metals touching the meat. We have maybe 10% of convection, which is all the air that goes up, very heated, very hot. And I will say we have all the rest, 85% via radiation, because if you recall, you will have coal, which is very red. Actually, it's radiating heat, and that radiation goes directly to the steak. So this is also common when you're in a, let's say, in a fire camp. Everyone is around. I will say radiation is the most, or the, let's say, how to say, the most important one, the highest, or the one that gives you more heat right here. Because convection goes up, and conduction, it's impossible because you are not touching the fire. Now that's for the theory behind that. Then we start analyzing the overall heat transfer coefficient for this right here. Because you will probably see here a tube, and we have, maybe it's like this. So we have plenty of that. We have this interaction, which is fluid and wall. We have the wall-wall interaction, and we have wall and inside fluid. So there are 1, 2, 3 layers. But typically, especially when you're analyzing very huge heat exchangers and you just care about what's the heat exchange rate or the overall heat coefficient, you will want to have an average of these three guys right here, and we call this the overall heat transfer coefficient. And you can have an overall heat transfer coefficient for anything, actually even also heat plates, whatever transfer media you may recall, you will have a overall heat transfer coefficient. Now we have also fouling factors, which is a very common practice, especially when we have high temperature. It's when small little things start to, let's say, attach to the wall. So you will experience higher speeds because there's less space, and higher drops of pressure, which means higher friction, which means more money. So you will want to avoid that. Now, that was the theory. We eventually want to do some unit operations, and I will say that the heat exchange is the most important one. It's the very basic theory of heat exchange. And what I mean with heat exchange is essentially just change of temperatures. No change of phases, just temperature. So you have solid, you increase the temperature of the solid. You have a liquid, you will increase the temperature of that liquid. You have the gas, you will have an increase of temperature as well. So we have plenty of equipment, but the most common one and typical one is the shell and tube heat exchanger, which is this one right here and this one right here. This one has no shell, and this one has a shell already installed. Now we then pass to the equipment and how do they work. So right now I'm not going to explain you how it works, but it's very important to realize that you will need to add some fluid here, and it goes here, and the tube fluid goes here. And you will understand the design, why this is like an hexagon, why this is round, how many holes, the size of the internal diameter, the outside diameter, the fluid flow, should you make it contra current or co-current, and so on. Then eventually we go to condensation, which is very basic or easy. Then evaporators is a little bit harder, but what I would say is the pain in the ass of these is the multiple stage evaporators, because you need to make a lot of iterations and so on. Of course, you will eventually do maybe a project or anything regarding these 3 or 4 operations and understand how much money you're expending with maybe one set, the typical set, and how much money you will save if you have more complex heat transfer operations. Now that was the what. Now let's analyze why do we need this, why heat transfer. And well, I think it's pretty obvious. Heat means energy. Energy means money. So that's essentially what we want. But also energy means transformation. If you are using a reactor, you need to cool it or heat it up. If you are doing, I don't know, maybe a mass transfer, you will need to add some heat or remove heat. That is the distillation column. And plenty of many other operations. Also momentum, just to give you one example of momentum, you will need to cool down before actually compressing some gases in order to decrease the energy input. Now, of course, we need to increase and decrease temperatures, maybe for safety or maybe because operation is required, or I don't know. There are plenty of cases. So you have this case, we want to increase the efficiency of this compression. Maybe you have a distillation column and it needs to be about 30 Celsius and you have a feed of 50 Celsius. Well, you will have to cool down that. How do you cool down? Probably with cooling water or air. More likely cooling water, because water is a very good coolant. We also are interested in the evaporation of material. Maybe we have a salt with water. We will want to maybe evaporate all the water and get the solid salt right here, and all the water, maybe even use it for drinking water. Condensed vapors, well, there are plenty of applications, food applications, typically also liquefied petroleum gases, which is a section of the distillate or the oil that help us to have a very clean flame in the kitchen. We also needed to design equipment. You don't know how to build a heat exchanger until you study them. So you don't know how many tubes, what's the better arrangement, should it be co-current, the heat and hot, this is, hot and cold, or should they be counter-current? To decrease fouling, understand the importance of fouling and why do we need to decrease it. And eventually you always want to optimize a process. So find the best temperature, or maybe if you have a vapor quality, that will be better. So that's essentially what I wanted to show you on heat transfer. Once again, I remember you guys that this is more typically for the chemical engineer. So this type of equipment you will see more often. You will see them more often in the chemical plant. So I know that there are plenty of manufacturing places that they might use other heating or cooling operations, but we are talking about chemical engineering, so these are the most common ones.